Okay, our next talk is from Takahiro Kushida, Professor Kenichiro Tanaka, Takahito Ato, Takuya Funatomi, and Yasuhiro Mukaigawa. The talk will be presented by Kushida-kun.
Yeah.
Please go ahead.
Thank you for introduction. I'm Takahiro Kushida from NICE. I'd like to talk about depth measurement technique by combining spatial phase shifting and time of flight. This is a joint work with NICE and University of Tsukuba. As you know, 3D sensing plays an important role in robotics, self-driving cars, and digital archive. In this work, we focus on the active 3D measurement methods. There are two typical and widely used 3D active measurement methods. One is structured light. The system consists of a projector and a camera and measures the depth from the distorted pattern of distortion of projected pattern. And the other one is time-flight camera, such as Kinect version 2. It measures the round trip time of light from the light source to the camera. Although they are different technology, there is a common feature. That is, both of them use modulated light and measure the phase of modulation. For example, the phase shifting, one of the methods of structured light, illuminate the scene with a sinusoidal pattern and measure the phase of sinusoid modulated pattern. Similarly, the time flight illuminates the scene with temporally modulated light by switching on and off the light source. Because both of them are based on the measurement of the modulation of the phase, so they have the common problem. They cannot determine the unique depth and suffer from ambiguity, as known as phase lapping. In this work, we propose to combine these modulations, as shown in the right image. By combining the spatial modulation and temporal modulation, we can obtain each two phases at the same time and resolve the phase ambiguity with these two phases and determine the unique depth of the scene. To begin with, we briefly explain about the method of phase shifting. The phase shifting measures the disparity between the projector and the camera by projecting a sinusoidal pattern. The depth can be calculated from the measured disparity by the triangulation theory. In phase shifting, this disparity can be obtained by measuring the phase of the projected pattern. And next, we briefly explain about the method of time of flight. The time of flight camera illuminates the scene by switching on and off the light of the light source. The temporal modulated light is reflected back to the camera with time delay due to the light path of the travel distance. The time of flight camera estimates the depth by multiplying the time delay and calculate the depth by multiplying the time and the speed of light. The time of flight camera measures this time delay at the phase of sinusoidal pattern. As shown so far, the phase shifting and time flight has a similar technique. They measure the phase by projecting a sinusoidal pattern. But estimating the depth from the sinusoidal pattern has an ambiguity problem. Basically, we cannot distinguish the phase phi and phi plus 2 pi because the same intensity is appeared repeatedly. So we can only know the phase phi of the sinusoidal pattern from the observation. This means we cannot determine the actual phase from the observation. The bottom illustration shows the relationship between the depth and the measured phase. The horizontal line shows the measured phase, and there are multiple depth candidates that satisfy the measured phase. This is the phase ambiguity. In other words, this one period less than 2 pi is the range of interest of this technology. The frequency of modulation is an important factor of the phase ambiguity problem. There is a trade-off among the depth resolution, the range of interest, and the number of measurements. When a low frequency pattern is used, the phase ambiguity can be mitigated, as shown in the left, because the slope of the relationship between the measured phase and the depth becomes gentle. The depth resolution becomes low, although the range of interest is wide. The blue horizontal bands represent the resolution of the measured phase, and the corresponding depth resolution becomes low, as represented by the wide vertical band. In contrast, when a high frequency pattern is used, the depth resolution is improved, as represented by the red band in the middle figure. But the range of interest that is determined by the interval of the phase ambiguity becomes narrow. This is a trade-off between the depth resolution and the range of interest. In most techniques, the phase ambiguity is solved by using multiple frequencies. By using multiple frequencies, the range of interest can be extended to the frequency of the greatest common divisor, but and the depth resolution is determined by the highest frequency. The right image shows the multiple frequency case. There are the multiple depth candidates for each frequency, but we can determine the unique depth that satisfies all phase measurement. This approach is very powerful, but the demerit of this approach is we have to take multiple captures and it sacrifices the real-time possibility. The bottom table summarizes this trade-off. Low frequency pattern suffers from low depth resolution. High frequency pattern suffers from narrow range of interest, and multiple frequency pattern suffer from the number of measurements. In this work, we aim to break this trade-off. The key observation of this research is the phase ambiguity is appeared differently on the depth domain because the disparity is inversely proportional to the depth, so the depth candidate of the phase shifting exists at increasing intervals. On the other hand, the depth is proportional to the time in time of flight measurement, so the candidate depth appeared at the same intervals. This is the big difference in terms of the phase ambiguity existence. So we use this difference to disambiguate the phase measurements. The method is quite simple. We illuminate the scene by spatio-temporally modulated light and measure the spatial phase and temporal phase at the same time. We can superpose the spatial modulation and temporal modulation because they are orthogonal. Simply saying, we can switch on and off the light of the projector. By doing so, the two different depth candidates are obtained simultaneously, and we can determine the unique depth that satisfies both phase measures. This means we can obtain a high depth resolution with wide range of interest at few observations. So the trade-off is broken. The effectiveness of our method depends on the selection of both spatial modulation and frequency and temporal frequency. If both of them are low frequency, that does not improve the depth resolution. So at least one frequency should be high. But in practice, there is no time-of-flight camera that works at high frequency, such as gigahertz. We have to build, so we have to use the combination of low frequency, low temporal frequency, and high spatial frequency. Once the temporal frequency is determined, the lower bound of the spatial frequency is also determined. The spatial frequency should be higher so that the depth resolution of spatial phase is better than the resolution of temporal phase. But it does not mean any high frequency is fine. There is an upper bound of the spatial frequency for a given time of flight frequency. The spatial frequency should be lower than the lower bound, so that the intervals of the depth ambiguity of the spatial frequency is larger than the depth resolution of the temporal phase measurement. We will a prototype system to demonstrate this method. The most challenging point is how to make the spatio-temporal illumination. The light source of the ordinary time-flight camera cannot project the spatial pattern, and the light source of the the projector cannot make a temporal modulation at megahertz. That is the frequency of time-flight camera. So we have to make a special projector system. The laser diode is, we use the fast laser diode and DMD, data mirror device. The laser diode is connected to the time-flight camera, and it is driven as like a light source of time-flight camera. So it can make temporal modulation. The light source emitted from the laser diode is collimated and expanded by the lens, and then spatially modulated by DMD. Finally, the spatio-temporal modulation is projected to the scene through a projection lens. And this is the actual projection system we have built. Okay, now we show the results. The target object is white planar board. The board is put at approximately 350 millimeters depth and slightly slanted. We compare the result among the ordinary time flight with low frequency, the phase shifting with only highest frequency, and the proposed method. The estimated value at the red line of each image is plotted below. In time flight, the depth is determined globally, but the details are very noisy. And in phase shifting, with single highest frequency, recover a smooth surface, but the unique depth cannot be determined due to the ambiguity. With our method, the depth is smoother than the ordinary time flight and globally determined. Some parts are still noisy because the disambiguation is failed. This is because the frequency of the phase shifting is set to the upper bound and near to the upper bound and beaten by the measurement noise. We think this can be sorry. We think we can recover this error by using a little bit lower frequency of spatial pattern. Okay. Finally, we discuss the limitation of this work. This graph showed the spatial phase and temporal phase along with the depth. The closing points have the same phase at different distance, different depths. So these points have the ambiguity. This is unavoidable with our method, so this is the limitation of this work. To avoid this, we can disambiguate the depth by looking neighborhood of the depth image. Okay. The bottom line of this talk is we can disambiguate the phase measurement by combining the spatial phase, spatial modulation, and temporal modulation. The key point is the ambiguity is differently appeared in the depth domain. By using our methods, we can recover the depth with high resolution with wide range of interest from few number of measurements. Okay, that's all. Thank you.
Right, we have time for a few quick questions.
How many measurements you need?
Measurements?
You said the number of measurements is fewer.
Ah,
How many measurements?
so for now we use only one measurement, one capture. But in time flight camera, the measurement they have subframe, 4 subframes. So we use only these 4 subframes.
So you don't need to shift the face mask. It's spatial.
Yes. So we have 2 ways to measure the spatial phase. So one is to shift the spatial pattern, and the other one is use the ratio of spatial intensity. We can use 2 pixels and measure the phase of the pattern by calculate the ratio of 2 pixels. So we can, it sacrifices the resolution of spatial phase, but we can obtain the spatial phase with only one image.
So maybe Mark, you want to set up. In the meantime, let me ask you one more question. This is a very interesting work to combine the structured light and time of flight together, and
Thank you.
totally respect the challenges in trying to implement a spatial light modulator at these high frequencies, temporal frequencies.
Yes.
My question is a little bit philosophical. It is one way of solving this problem is to use just temporal modulation and then doing like the Chinese remainder theorem. So Mohit Gupta had a very nice paper where he talks about the fact that you can use only 2 frequencies to do this as long as the 2 frequencies are close together, right?
What? Sorry, could you say sorry?
So you talk about how if you just have temporal imaging and you want high resolution, you talk about how there might need to be many images that are captured. But ignoring some noise analysis, there are methods where you can use, let's say, 2 sets of images at 2 different frequencies. Have you considered how your approach might differ from that in terms of a performance situation?
Sorry, I
So
don't understand this question.
My apologies, but in short, the
Short. Oh,
idea is basically that if your two frequencies are close enough together, you might not need that many images if you just use temporal phase unwrapping. It's something we can discuss offline, but it would be interesting to see how your system would compare.
Sorry, I don't
We can discuss offline.
Sorry.
Once again, great work. Let's thank our speaker.
Thank you.